last talk for today and also in fact the conference, but not quite Swiss time. So, but let's introduce Henrik from Berlin on universal operations in resource theories and local thermodynamics. So, thanks.
Well, thanks a lot. So thanks everybody for actually coming back after the very last break of the conference to hear this talk. So yeah, I'm a bit under pressure with having my boss as a session chair. So, so as you see, I will talk about thermodynamics, and actually this title is a bit in reverse order. So I will talk a lot about thermodynamics, a bit about local thermodynamics, and then, well, even less about universal operations in resource theories. But still, I hope you like it. So when I speak about thermodynamics, it's a bit different from what we have mostly seen in the conference so far. So what I think of is more something like this. So you have like a steam engine and a heat bath, and you want to kind of raise a weight or something like this. Oh, and I see that actually the titles are cut out again. Well, okay. And so thermodynamics, like in the traditional sense, was actually invented to understand these kinds of machines and to understand how far can I actually raise the weight with a given heat bath at a given temperature. And recently people have, well, of course, become interested in whether we can sort of extend this into an operational theory for small systems and individual systems as well. So we would like to think now of more of systems like this. So two-level system, actually. Now, you can't see it, but on the top, there's a title called Quantum Thermodynamics. But for the moment, I would just like to talk about this as a classical two-level system, so just a classical bit. But since we also talk about energy in thermodynamics, we have to consider as a state of this bit, which describes this bit, not just the excitation probability, but also the energy gap. And similarly, as in the last slide, I can just then ask the question of, what can I actually do with such a system? What kind of work could I perform once we have something like a heat bath next to it? And instead of considering a weight that is lifted in this small scale setting, I would like to consider, well, think about this as a battery that's somehow being charged while doing operations. And well, to meaningfully ask what we can actually do and how much we can achieve for certain tasks, we have to properly specify the operations that we are allowed to do and also the cost of these operations, like in resource theories. So there will be, in this talk, there will be two kinds of operations that we will consider. One type will be something which we call a thermalizing map. So we bring the system in contact with the heat bath, and then something happens to the state of the system. So in this example, the probability of the excited state. And for a general quantum system, this will just be a quantum channel. But I will talk later about the precise details of what happens for these thermalizing maps. And the other thing that we can do is to somehow wire the system to a battery and then change the Hamiltonian of the system. So here we can change the energy gap. And we will assume that the energy that is, well, I mean, the system has a different energy now because of this Hamiltonian change. And we will assume that this change of energy will flow into the battery or will actually come from the battery. But we will not explicitly model the battery. But as so the picture to keep in mind is that when we change the Hamiltonian, we somehow charge or decharge the battery. And if you would have instead a general quantum system here, we would be allowed to change the Hamiltonian over time. So effectively, we will have some unitary dynamics on the system so that the initial state, rho 0, goes to some different state. And also the initial Hamiltonian goes to a new Hamiltonian, h sub t. And this charges the battery by some amount of work. And we always measure work here in expectation value, so on average. Okay, so in the rest of the talk, we'll be concerned with how do the assumptions that we make while having the system in contact with the heat bath affect the amount of work that we can perform, and also how do the possible Hamiltonians that we can actually realize in the lab perform, and how do these two assumptions interact. Okay, But to explain this, let me somewhat change the representation. So from now on, well, you will see this picture many times. So here I plot the excitation probability over the energy gap of the system. And the yellow dot represents the state of the system. And this red line is just the line of thermal states for a given temperature. So for each Hamiltonian, since we have some fixed temperature, we can associate the thermal state, so just the Gibbs state. And this is this red line. Okay. And if we change the gap of the system, well, we somehow move horizontally in this picture. And the work that we extracted is just given by this area under the curve in this representation. We could also go into the other direction, and we could get a different sign for the work. But now what happens when we actually bring the system in contact to the heat bath? Well, we will consider 3 different possibilities. The first and simplest one will be what we call weak thermal contact. And this just means that the system is actually brought to thermal equilibrium. Okay? So the state of the system is changed to the Gibbs state of the system with respect to the current Hamiltonian. So this always depends on the current Hamiltonian, and this is very important to keep in mind. In this picture, it just looks like a vertical jump to this isothermal. But now you might object, well, this is nice, and this is also what has been done previously and traditionally in statistical mechanics and thermodynamics. But somehow, if we have small systems and we have a good lab, why don't we allow for more general operations? And specifically, you could ask, why cannot we do the following, which we'll call a thermal operation? So a thermal operation is, well, you're allowed to take any heat bath Hamiltonian, which you can choose yourself, but it has to be in the Gibbs state. And then you're allowed to do any joint unitary that actually is energy conserving in the sense that it commutes with the total Hamiltonian. And then you trace out the heat bath. So actually, you will always take a new heat bath if you want for this. And this is great. This allows you to use all your knowledge about the microscopic details of this heat bath Hamiltonian. It could be a very small scale system, it could be a large scale system. You can actually precisely tune the interaction between the system and the heat bath during this operation. And of course, the set of operations that you get is much, much larger than just weak thermal contact. But in fact, we will consider an even larger class of operations. And this is the following. This is what we call a Gibbs preserving map. So this is basically anything that does not bring the system out of equilibrium if it's already in equilibrium. So you have some state rho and Hamiltonian H, and the effect of bringing the system in contact to the heat bath is given by some quantum channel G sub H, such that it has the Gibbs state as the fixed point. Why do we need this? Well, if there would be states or Hamiltonians for which the Gibbs state would not be mapped to the Gibbs state, then we can bring thermal states out of equilibrium for free without paying any work and just use this as a source for extracting more work. So we could basically get out infinite amounts of work. So we could build a perpetuum mobile. Okay, so this is surely a necessary condition, and this is arguably the most general kind of operations you could allow for in any sort of operational framework of small-scale thermodynamics. Okay, so how does this look like in this picture? Well, one thing you can do is to just map the state a bit below this isothermal. So this might or might not be useful. We will see later if it is. Another thing you could do is actually to map the system a bit above this isothermal. This is a bit surprising once you think about it, because it means that you have some system, it has some temperature, you have a heat bath at a higher temperature, and you can actually bring the system to a temperature which is even above the temperature of the heat bath for free. And this does not violate any second law. This ensured by the data processing inequality. And so the distance you can go above this isothermal is actually limited by the free energy. So this ensures that we cannot just violate some sort of second law in any way. Okay. So this is what we can do with our operations. So this is all nice and good. So let me summarize these different classes. So we have weak thermal contact, and this is certainly a subset of thermal operations, which again is actually a strict subset of Gibbs preserving maps. This has been shown. Okay, and now we ask, how much work can we actually extract from a given system? And I would like to present this as a game between me and you. And this is the title is the game of work extraction. So it works like this. So you start and you pick some initial state in Hamiltonian. So this is up to you. You can choose whatever you want. Then you apply some unitary dynamics. So dynamics generated by some time-dependent Hamiltonian. Then you apply some Gibbs preserving map. That's up to you. You can choose it. And then you can actually repeat this finitely many times. Okay, and after some time you decide, oh, let's stop, this is good. And the only requirement is that the final Hamiltonian is the same as the initial Hamiltonian. Otherwise we could not fairly compare how much work was actually extracted. And then you actually, in the end, you have extracted some amount of work, and we'll call this W sub GP. And as I said, it's a game between you and me, and we both want to charge the battery as much as possible. So I will now play the same with just one difference. I have actually much worse rules than you have, because the only thermal free operations that I have are weak thermal contact. So every time I bring the system in contact with the heat bath, it just thermalizes, whereas you can just really use everything you know about the heat baths and choose your heat baths yourself. So to make up for this, I win if I do as good as you. Okay, so if I can get at least as much out of the or into the battery as you can, I will win. So the question now is, who wins? Well, it turns out if you begin, I will always win. So this might be a bit surprising because you have much more freedom in your operations and you can use all this knowledge about the heat bath. Well, actually, if I begin, you also win. So the two operations are exactly equally powerful for work extraction. So why is this? Well, the theorem is this. The work yield of a cyclic Hamiltonian process using these GP maps can be bounded from above by the relative entropy between the initial state and the thermal state that corresponds to the initial Hamiltonian. And you can rewrite this in terms of free energies, and then you basically get exactly the same bound as you get in phenomenological thermodynamics for work extraction from a fixed temperature heat baths. But it actually turns out that this bound can be saturated arbitrarily well already with weak thermal contact. And let me show how this optimal protocol works. So again, we go back to this picture. So we have some initial state represented by this yellow dot. And the very first step of the protocol, of the optimal protocol that extracts the optimal amount of work, is to find a Hamiltonian such that the initial state looks like the thermal state of the initial Hamiltonian. And then you change the Hamiltonian to that new Hamiltonian. So in the picture, it just means you move this yellow dot horizontally to the red line, like this. Now, this will actually cost some amount of work, because you are increasing the gap of the bit, but you don't change the excitation probability. But now the second step of the protocol consists of going back to the initial Hamiltonian, because you have to go back in some way or the other. And you do it by going along this red line, so this isothermal line, like this. And in this step, you actually extract work, and the total amount that you extracted is just given by the difference. So it's this area. And turns out that this is exactly the relative entropy between the initial state and the thermal state to the initial Hamiltonian. Of course, you cannot do this exactly in any finite protocol, because you can only move horizontally and vertically. But you can approximate this arbitrarily well. So for any epsilon that you extract, which is less than the optimal value, I can extract a bit more, so I always win. And in this sense, we say that weak thermal is universal for work extraction. Okay, now you might object, this is actually a rather boring game, because I always win and you always lose. So let me propose to change the rules a little bit. Okay, so we can imagine a situation in the lab where actually we cannot increase the energy of the system arbitrarily high. So there will be some critical value of the energy gap, and above this, well, you cannot go above this with our Hamiltonians. So there's this huge red forbidden region, okay? So let us see what happens if you impose this restriction. Well, let's first look at what I could do. So I could first change the Hamiltonian, so lower the energy gap, because I cannot increase it, and actually extract some work. But at some point, I will have to thermalize and go back to the initial Hamiltonian. And it turns out, it's very easy to convince yourself that in the end, I will always extract a negative amount of work. So actually, I cannot do anything. So the best I could do is do nothing, again, and extract 0. So this was when I first changed the energy gap. I could also just first apply weak thermal contact, but that's of course useless because from a thermostat you can never extract any work. So what about you? Well, I told you that with these Gibbs preserving maps, you can actually jump above the isothermal, like this. Okay, let's do this. But now, to actually do the optimal protocol and do the very first step of the protocol, you don't have to increase the gap, but to decrease it, right? Because you want to go to the red line in a horizontal way. So you can do this, and you extract some amount of work, and now you have to go back to the initial Hamiltonian, and again, you just go back along this isothermal, like this. And in total, you have extracted some amount of work. So this means that under this restriction, you can actually win. And weak thermal ceases to be universal for restricted work extraction. So this was a very particular and simple example of one classical bit, actually. So we could consider more general restrictions on the Hamiltonians that we can prepare in our lab. So from now on, we will introduce the set H, which depends on the initial Hamiltonian. And this will be the set of allowed Hamiltonians, those that we can actually implement in the lab. And then we can derive a new bound on the work that we can extract using weak thermal contact, and looks like this. So we have the optimal value that we have without the restrictions, and then we have a penalty term, this one. And the U here is a unitary which is taken from the unitary group that's generated from all the allowed Hamiltonians. And what this term really says is, well, we have this very first step in our protocol, in the optimal protocol, and this term really just measures in how far we actually fail to do this very first step. So in general, we will not be able to find a Hamiltonian anymore such that the initial state looks like the thermal state to the initial Hamiltonian. And this term precisely measures this. Okay, so this is all nice, but so let's have a look at a more interesting restriction than just an operator norm. And to do this, suppose you have an interacting system in your lab, but you can only change the on-site terms, so the on-site Hamiltonians. I mean, this is a very realistic scenario. Usually we cannot just arbitrarily change the interactions between subsystems. So this set, which actually really depends on the initial Hamiltonian, as you see here, models the situation of local control over an interacting Hamiltonian. So this would be the situation which we think would properly define what we would call local thermodynamics, because you can only have local control over your systems. Okay. Now, then the theorem is that, again, under this restriction, there are situations where using weak thermal contact, we cannot extract any work, whereas with Gibbs preserving map, we can actually extract work. So again, you would win in the game, and I would lose. So how does this work? Well, actually, the proof is quite simple, so I can show it to you. So we'll just consider two qubits, which are initially maximally mixed, and I will denote this by this big omega. And the initial Hamiltonian is just a Pauli Z tensor Pauli Z. And the initial temperature is, well, we just choose this to be 1. And we can also assume that all the Hamiltonians that we consider are traceless. This will simplify the proof a bit. Then we can use our general bound to upper bound the work that we could extract from this initial state. And we can rewrite it like this. But now observe, since the initial state is maximally mixed, this unitaries can actually be dropped. So they are not useful. So let's do this. Okay, so this is already quite nice actually. But it's even nicer once we rewrite this in terms of free energies. So we have seen this during the conference several times, that the relative entropy between a state and a Gibbs state can be written as the free energy difference of the state with respect to the Hamiltonian of the Gibbs state and the thermal free energy of this Hamiltonian. So let us do this. So actually there are two terms with the, well, you would expect 4 terms here, but 2 of them cancel because the state is the maximally mixed state and Hamiltonians are traceless. Okay. And now we'll play a simple trick, and this trick is given by the Payal-Spokal-Lyubov inequality, which unfortunately you cannot properly read. But it says the following: if you have a sum of 2 Hamiltonians, then the free energy of this is upper bounded by the free energy of 1 Hamiltonian plus the thermal expectation value of a second Hamiltonian with respect to the first Hamiltonian here. But now we have chosen a special initial Hamiltonian, which is Pauli Z, tensor Pauli Z, and it turns out that the Gibbs state of this Hamiltonian is actually Hilbert-Schmidt orthogonal to every local perturbation that we can add. So this term always vanishes, and we can just upper bound the free energy of any other Hamiltonian in the set of allowed Hamiltonians by the initial one, this one. So we plug this in, and we get, well, the free energy of ZZ minus free energy of ZZ, which is 0. So I cannot extract anything. What would remain to be shown is that there is actually a Gibbs preserving map which maps the initial state to some useful state. Okay, and this can be done using what's called thermomajorization. This is a generalization of usual majorization, which you know from entanglement theory. But I will not show the details here. But you can do that, and you can show that if I look at this Hamiltonian, so ZZ plus a bit of on-site Z, you can actually map the initial maximally mixed state via a Gibbs preserving map with respect to the Pauli Z, tensor Pauli Z Hamiltonian to this state. But now, this Hamiltonian is in the set of allowed Hamiltonians, and that means we can just use the optimal protocol to extract whatever we could extract from this state, usually. And this is just given by the relative entropy, which is positive. And that's the proof. Okay. So to summarize these restrictions, well, we have restrictions on the Hamiltonians, and these lead to what we call passive states for weak thermal contact. But these Gibbs preserving maps, which are useless when we don't have any restrictions, actually activate such passive states, at least sometimes. And therefore, weak thermal contact ceases to be universal under these very natural restrictions that we put on the Hamiltonians. So in the last few minutes, I would like to put this into more broader perspective. And for that, I would like to roughly define what I understand as a resource theory. So resource theory is basically a class of operations that is closed under composition and contains the identity. That means the doing nothing operation. And it has some distinction between free states and free operations. And so in a sense, a resource theory just models any restrictions on what you can do in an experiment. So a natural question to ask then is, what happens if you try to combine 2 of these? So we have 2 resource theories, A and B. I mean, someone would like to know what happens if we want to impose both of these restrictions. And when we started this project, well, we chose one of them to be thermodynamics, and we were actually interested what happens if we try to combine thermodynamics with locality. So this would be B somehow. And then you can, well, define the following property for resource theories. So you can look at a subtheory, so a proper subtheory, B in A, and you can say that it's universal for a specific task. It's very important that you have to specify a task. If this task can already be achieved optimally only with operations from B. Observe that this is different from, say, a universal gate set. We don't ask that the operations from B actually generate all the operations in A, but we actually have a closed subtheory, and it's just universal for a specific task. Okay. So now suppose that we have a subtheory A prime, which is universal for some task. It sits in big A, and we have a different subtheory B, which somehow intersects with A prime. Then we could ask, is the intersection of A prime with B still universal for this task that we have specified when we compare it to just B? So if we do this. So in our example, the whole thing was thermodynamics with Gibbs preserving maps, and the task was work extraction. A prime could be chosen as, well, weak thermal contact and was universal, and B was the subtheory that you get when you restrict your Hamiltonians. And we saw that, well, weak thermal contact loses its universality once we impose additional but natural restrictions. So I think the basic take-home message is here that even though you show that in principle there are some operations which are universal and which allow you to do anything arbitrarily well, once you impose natural restrictions, this can easily fail. So what are open problems or open questions for this? Well, of course, can we find similar situations outside of thermodynamics? And I think in several talks this week there were situations which potentially could be of this form once we formulate this in this language. Then there are operationally meaningful types of restrictions which are not captured by Hamiltonians. Say you could imagine that you can only do a finite context to the heat bath. Then this would probably also lead to a phenomenon like this. And finally, well, you cannot read this again. Well, but what about what is called single-shot statistical mechanics? So we have here measured the work in expectation value, but there are also different frameworks of thermodynamics where we actually do single-shot work extraction. And the question is, how can we sort of generalize this to such settings? And with this, I would like to thank. Thanks a lot for the organizers for letting me give this very last speak. Thank you.
Yes, thanks so much for this exciting talk. I'm sure there are questions, yes.
Okay, thank you very much for this clear presentation. So I want to ask two questions. First of all, you mentioned in the open question that you could also imagine having only finitely many contacts to the heat bath.
Yes.
So do you have any knowledge about the convergence rate that would then occur in the limit of n going to infinity towards the optimal value of the extracted work?
No. That's the short answer.
Okay. Then the second one, you mentioned in the beginning that you characterize your state in terms of the energy gap,
Yes.
and in terms of the excitation probability.
Yes.
So this excludes coherences. Have you also thought about coherences and how you could implement those into your framework?
Yes, well, with coherence, so maybe for the non-experts, there's an ongoing debate in thermodynamics whether you have to consider coherences as a resource. Well, in this talk, actually, all the states that we considered were classical. So actually, I mean, everything that I did was actually classical. There was no real quantumness involved. So everything that we did could have been done with thermal operations only. And therefore, you don't really need to think about coherences that much, I think. Of course, once you want to actually implement this unitary dynamics, this time-dependent unitary dynamics in a sort of closed box fashion, where you don't actually do this control by hand, but have some sort of timing device which does this, well, as you know the best, this would need some sort of source of coherence. But in our framework, this is completely outside of the framework, so we don't really worry about it.
Okay, thanks.
Are there any other questions? So that's not the case, then let's thank the speaker again.
Thank you.
But it's not over before it's over. I think as a very last